Okay. So, hello everyone. Today I'm going to be talking about our research project for the machine learning course unit. Our project proposal is prediction of latent tuberculosis risk for optimizing preventive treatment allocation in Uganda. Well, first of all, let me explain to you what latent TB is. Well, latent TB is some sort of dormant tuberculosis. It's a bacteria within you, but it's dormant and it's very hard to be detected in the body. So ideally, that is a very, very risky disease because there are chances that it will progress into active TB and it is very deadly. And once it is not treated, it will lead to massive deaths. Well, our project is kind of centered around Uganda and how currently the Ministry of Health is handling it. So our group members, we are three. Pangama Ben Joseph, we have Nachas Farida, Takoza Michael Owen. This is our intro, this is our guideline for how we are going to present our project. Well, as I said earlier on, Uganda has millions of cases of latent TB, and these dormant cases serve as a primary reservoir for future active TB outbreaks. Uganda's fight against tuberculosis has reached a critical bottleneck, while the National TB and Leprosy Program has improved the treatment of active cases, yet still the country faces a visible burden of latent TB infection. The Ministry of Health operates with a limited budget, and therefore sometimes it kind of supplies resources to areas based on like population density rather than areas that have a high prevalence rate of latent TB progressing to active TB. So basically what our project is going to do, we are going to build a machine learning algorithm that is going to be in position of utilizing multiple data sets countrywide, and we are going to use these data sets to come up with a dashboard that is in position of providing detailed information to the Ministry of Health that tells them that in such and such an area, there is a high risk of people with active or people with latent TB having a high risk of getting active TB. So one of the related works we based our project on is a study by an author called Augustus Atrinde, and in his research, he says that there is a high burden within high-risk populations with prevalence rates estimated between 16% and over 50%, depending on the group that has been studied. And then also on a very recent study, it shows that during the active cases of TBs increased from a value of 29,640 to 72,768 in 2024. And this is a very, very large increase. This shows you how dangerous TB can be. And well, let me pass on to my colleague, Najaz Farida, to explain the remaining part.
Yeah. The research questions and objectives. So here we ask ourselves, which districts in Uganda show the highest risk of latent TB converting into active TB? That's where I want to put our primary focus and come up with a model that is going to easily identify the districts without having to go through a long procedure of visiting and recording and seeing, but you're going to train it based on the recent data. And the objective, of course, is to determine the special or temporal trends of TB cases across Uganda, those particular districts in general, using the data sets of DIS2. Yeah, so the next question is, what patterns exist in TB trends across the districts using DHIS notification data? So here we basically want to identify like the hidden TB risk patterns and high risk district areas. We want to know in Uganda which district is having recent history of TB, of latent TB. We want to identify how the cases of TB have been solved previously, what needs to be changed, and how is it going to help us in building our next model? So we also ask ourselves, can my machine learning model identify the high conversion TB risk in districts? Of course, the main goal of this project is to model a final project that's going to predict the risk of latent to active TB using the machine learning algorithms we are going to be using in this project. And then the fourth one is to how effective is the machine learning dashboard in supporting TB preventive treatment. So at the end of our project, we want to come up with either a dashboard, a web system, whatever we shall discuss with our government. And this dashboard, we want to know, is it going to be accurate? Is it going to give the healthy worker concerning TB accurate results? Is it going to give the correct district that is having high TB? Is it going to be very effective? We want to know that at the end of the day. So the next slide is the research contributions and outputs. Well, here, the research contributions we managed to get from the data sets. There were very many data features that were useful in coming up with the EDAs, the exploratory data analysis, and we managed to come out with visualizations like the k-means cluster map, the correlation map. We came up with the age 6 pyramid, and this one basically shows between which age range is the latent TB highly going to be found or discovered, and it's going to convert to active TB. We managed to see here that which sex group, is it the female, is it the male, that is going to be having a high risk to latent TB converting to active TB. So yeah, the research outputs here are basically the EDA visualizations, which present data in a more meaningful way and a more understandable way, as you're going to see in the next slides coming down. And yeah, here, this one is in form of the next steps you're going to develop.
So my name is Kakoza Mike Cohen, and I would like to take you through the dataset description and exploratory data analysis. So these are the datasets we are able to get. The prevalence survey of 2014-2015, which included the community tuberculosis burden, the missed latent cases, and the age 06 distributions. Then we had the DHI S2 tuberculosis notifications of 2020-2025. It included the facility reported tuberculosis cases, the district level trends, monthly case counts, the NTLP annual report of 2023-2024 included treatment success rates, program indicators, national targets, and the WHO World Health Organization tuberculosis country profile. That one included the global tuberculosis indicators, the Uganda performance metrics. So these data sets, they were about different things that we had to show visually in the next slides. And being EDA or exploratory data analysis, these were to help us statistically clean the data before modeling it. So whatever visualization you are to see, which lies under a correlation heat map for risk factor relationships revealing what causes tuberculosis risks, the k-means clustering, which is for grouping, and this grouping comes to population risk segmentations per districts. Those are districts with the highest population cases of tuberculosis vis-a-vis other districts. The Pareto chart for resource prioritizations. These are fundings that come from the government, but also from other external bodies like WHO, United Nations AIDS Program Fund, and many others. Also, the age sex pyramid, that is to male or female cases, but the population in the country. So all that is to be shown in these next slides of the visualization. So this is our heat map. And as you know that a heat map is for different variables. So one of the variables we looked at was the age. Secondly, was to the point, as we have mentioned here, that the risk relationship factors of what causes tuberculosis. So one of the things we got from our data sets were that most of the people with HIV/AIDS are the ones who have the the highest cases of tuberculosis. So in our correlation heat map here, we look at it in via different age gaps, look at it via the symptoms, those are the ones that are in relation to those with AIDS, and we look at it via to the rate in the different geographical areas of the country. So then we are able to indicate the risk factors as you see by the color chart here. Those who are typically red, slightly close to orange, and so on. So when it comes to the K-means cluster, as I said here, we are grouping, and the tuberculosis risk factor we are grouping at is per population in the different districts. So we group and then we rank. As we also said to the other side, there's the heat map factor. So here we group and we also rank. So to continue to the next one, we have a cumulative curve or cumulative graph. This is the Pareto chart, and this is at the tuberculosis case count. So this is the case count per district, and therefore it gives us that which districts at a high at the front line of high risk factor. So we also looked at the population prevalence bubble chart. This is the one for looking at the population of the different people per district. We looked at district because the data sets, we were able to group them down to geographical areas in Uganda and the various districts in Uganda. So it also talks about the HIV prevalence. As I said, this disease is rated with HIV/AIDS. So the age sex pyramid, male versus female, of course, as you see here, that the younger generation, 15 to 24, suffers more than the elderly. We talk about the funding gap. Yes, the concentration of the fundings is mainly at the point of districts with the higher population, unevenly to the districts with the higher risk factor. Those two things are different, population and risk factor. So the gap accumulated up to $6 million. That is roughly around 40 billion Ugandan shillings. But I said most of this money even comes from fundings abroad. So the conclusions we are to make that, of course, I talked about it. Most of the people with HIV are the ones with the tuberculosis infections and are the ones at the highest risk point. Yes, the EDA, the EDA helped us to understand that structure and characteristics of tuberculosis data sets, the visualization that we did there. Also, we had to create a dashboard, which is to help health officials easily view the risk patterns and hotspot districts. The limitations to all that came to the data sets were old. You have those of 2014, those are 10 years ago. Then also the limited understanding of the predictive patterns. Predictive patterns, these also hindered us because when you look at the point that most of this data is just statistical. This data is it is analytical in a way that data that was got from these data sets was mainly for what the government had. So these are the models that we are to use: PCA, random forest, Bayesian network, the RF handshake, and SVM policy and validation. So acknowledgements, we'll go back to our Dr. Gariwango Marvin, Lecturer, College of Computing and Information Sciences, Allison.com, specifically for logic of learning, and the fail-fast protocols shaped the foundation methodology of this work. Dr. Efrens, lecturer, for the invaluable guidance and support for that. Thank you for listening to me.